Hello, in this video we are going to see some basic aspects of graphics and sound encoding. So basically in this unit we have seen that we can convert numbers and represent those numbers with bits. It can be applied to different types of numbers. It can also apply to symbols like in text, and it can actually be applied to any kind of information, because as we know, today's computers work with any kind of information, but in the end everything has to be converted to some kind of binary code. So anything needs to be encoded, like graphics. When you see an image, this is a photo with some flowers. If you take attention to the details, when it's a digital image, actually the image is composed of small points that are called pixels. That's where the megapixels in our digital camera, like in our mobile phone camera, come from. So actually the image is a set of points, each point of a single color. If we put so much pixels in the picture, and even if each pixel is a different color, when we look at the image, and if the pixels are small enough, we cannot distinguish the individual pixels, but we see a continuous photograph, okay? But it's actually a discretization of the information. So when we encode an image, we basically have some horizontal size, a number of pixels in the horizontal direction, a number of pixels in the vertical direction, and for each pixel we need to encode the color of the pixel. We need to express the color using numbers. So there are many different ways to actually encode that color. The way that most display units use is a combination of three basic colors. Because of the nature of our eye, we can combine basic colors and make our eye and our brain believe that this combination is a completely different color. So for example, our most typical screen monitors have small points. Each pixel in a monitor can include some source of red light, green light and blue light. By working with the intensity of these three components, we can build any color. For example, if I put a very intense red light, slightly darker green light and darker blue light, and I combine them all them together, I get a color like more or less like this, like a kind of orange. Okay. Now to represent the quantity of each color, we use some number. One very common option is using 8 bits for each color component. So we can have a quantity that goes from 0 to 255. Okay, so this color could be the 255 in the red component, 172 in the green component, and 44 in the blue component. They all together make that a color of, or kind of orange color that you see here in the picture. So to represent this color, we are actually using 8 bits for the red, plus 8 bits for green, plus 8 bits for the blue component, equal to 24 bits for each pixel in the image. Imagine that we have an image that is 640 pixels wide, and it's 480 pixels in the vertical direction. Okay, so the number of pixels is the size, the horizontal size times the vertical size, and each pixel will use 44 bits. So that way we can calculate what is the size of my image. Okay, the width times the height times this is the number of pixels, the number of bits needed for each pixel. So it will be the size of the image in bits, and we can then convert it to bytes or megabytes or whatever. Okay, so in the end my image is just, you see this 24 bits. When it's stored, it's just a long sequence of 1 and 0s packed in 24 small 24 packets. Okay, also I told you about the encoding with red, green and blue components. It's not the only way to encode color using numbers, using bits. Actually, for images sometimes, and especially for video images, there are other ways to encode a color. Instead of using 3 components, we may use some characteristics of the color, like the brightness, like the or the intensity of the color, like the type of color, if it's red, if it's green, it's and also the saturation of the color, is meaning if the color is more red or less red, or is more green or less green. If you use some kind of image manipulation program, okay, this is the GIMP, quite well-known manipulation program. These programs allow you to select colors with this kind of panels that allow you to select colors in different ways. For example, here I can select a color using combinations of red, green and blue. This is the color I have selected. You see, when we have similar quantities of color, I have something like a gray. White color is all the components at the maximum. Okay, black color is all the components at the minimum, no light at all. Any combination that has all the basic colors with the same quantity, it's the balanced combination of all possible colors, which is what we see as white or gray color. If you want something slightly red, you can increase the red component a little bit and you change your color to red. If you want something slightly blue, then you increase the blue color. If you want something between green and blue, you put some green and some blue, and you have this kind of light blue here. But also these programs with these programs you can select your color in a different way. For artistic purposes, it used to be easier. For example, here in these sliders, you can select the quality of the color, with type of color you want. If you want a blue, if you want a green, a yellow, a red color, let's say we'll go for the green. For the yellow, it's around here. And once you know you want some kind of yellow color, then you, with this position here, I can make it more yellow or less yellow. Okay, very light but more soft yellow, or very light but stronger yellow. Okay, so it's these programs include this type of exploration. There are some calculations you can do with raw graphics, with images which have no compression. Okay, and there are also some definitions. The color depth is the number of pixels, the number of bits you use to encode color. We have seen 24 bits in our example. This is a very common number of bits, and it's called full color. Okay. Now we have the number of pixels in my image, which is the pixel width times the pixel height, as we have seen. With that, we can calculate the size of the image. It's called the raw size because it is the size occupied by all the bits without compression. In many typical formats, we use some kind of compressions for images, like in JPEG format or in PNG format. So if you do the operations, probably the size is going to be bigger than the actual size of the file, because most these formats use some kind of compression. Okay, but if you want to check, you can open an image and save it in some kind of bitmap or pixmap format using some software, image manipulation software. These formats used to be not compressed, and you can do the calculations and compare the size of the file with the calculated size of the image, and you may check if these are the same or not. Another important factor with images is the resolution. That is the relation between the pixels and the real size of the image. It means how many pixels you have for some real length. You may have a horizontal and a vertical, different horizontal and vertical resolution, but they are normally the same. Okay, and it's also good to understand that when you have a higher resolution, then it means that you have more pixels in the same size, so the image will look more real. It is considered that for printed images, something you have in the paper, something like that, a resolution between 150 and 300 dots per inch. Dots is like pixels per inch is a good resolution for good quality printed material. Most screen monitors used to have around 90 dpi resolution. Okay, so this is more or less what you have. You can see that for if you know the size, you know the size of the image you want to print, or if you want to represent, and if you have the resolution, then you can calculate what's the horizontal number of pixels and the vertical number of pixels. And it can be good because sometimes we use images that has so many pixels that the pixel count is too big. Okay, so for example, in a typical monitor you will normally see around 2 megapixels, 2 million pixels. A regular monitor is about 2000 times 1000 resolution, more or less. Okay, this is roughly 2 megapixels. So if your camera or your mobile phone camera can make images of 10 megapixels, you must know that you are missing most of the pixels in your image. So if you are always if you include one image in a document, like a presentation like this, okay, you don't need a 10 megapixel image. Yes, a 2 megapixel will be more than enough. So you can lower the resolution and make your file size smaller. Okay, this is just some basic aspects, but our intention is to understand that all these numbers in the end must be coded in using some kind of binary code.